And it's my pleasure to introduce the first speaker of the session, Daniele, who will be talking about adversarial training with cycle consistency for unsupervised super resolution in endoscopy imaging. The floor is yours.
Hello, everyone. I'm Daniele Ravi. I'm from UCL, and today I'm going to talk about our recent work on unsupervised super resolution for endomicroscopy. According to a recent report made by the Global Health Organization, cancer is the second leading cause of death globally. Many cases today of cancer are still discovered in an emerging stage in the hospital, and for these cases, the expectation of life is only 1 year. Early detection can greatly improve the expectation life. How we can do early detection? Usually, the GP, during a physical examination, if finds something suspicious or there is something abnormal in the images, in a scan image, suggests to do a biopsy. Biopsy is a procedure where the surgeon removes a small a small tissue from your body, and he sends the tissue to a special lab. And after days or weeks, the patient and the GP receive a histology result. This is a gold standard for the diagnosis of the cancer. However, there are some limitations here. The first is that the patient and the GP receive the feedback after days or weeks. And moreover, if the tissue is deep inside the body, the surgeon may use some image guidance to better identify the area of interest. A recent image modality is called biopsy, and it allows this image guidance, and it allows also to perform optical biopsy. What is optical biopsy? Optical biopsy is generate images that are histologic-like images, and therefore the surgeon have a feedback in real time. And this can help the investigation of the tissue be performed better. And moreover, the patient can receive instant feedback and eventually a possible diagnosis. However, correct diagnosis and related treatment are hampered from the fact that this device produces images with low quality. Low quality means that the images have noise, have low contrast, and have artifact. In the last few years, some progress has been made on the hardware of this device. However, the physical constraint and how the acquisition process of this device works still limited the final resolution. So a valid alternative is to use a post-processing approach that somehow remove all these problems. And this can be done applying, for example, super resolution algorithms. Exploiting the success of deep learning, we thought, okay, we can use Exemplar-based super resolution, that is a deep neural network that takes into an input low-quality images and paired high-quality images to train this network. And specifically, the algorithm go through all the patches in a training database, extract paired patches, and extract some feature, and create a model that can map the low-quality images to the high-resolution images. This approach works fine when there are available camera that can generate these high-quality images here. And the low-res images can be derived, for example, downsampling the iris or adding noise to the iris. In our context, we don't have the high-res images due to the limitation of the device. We have only the low-res images. And deriving the high-res images from the low-res images is not simple. So we thought we could modify the original example-based super resolution approach. Instead of having paired of patches, we exploit high resolution images from an external domain and try to transfer the super resolution from this external domain to the initial low-res images. Now the problem here is that the network again go through all these patches, and the patches are not anymore aligned. That means that the network can train to generate high-resolution images, but this doesn't mean necessarily that these high-resolution images represent the initial low-res. So we had to add an extra block that forced the network to generate images that represent the low-res. And this is made exploiting some physical properties, how these low-res images are acquired. And I will explain this in a bit. In this slide, I'm going to show our pipeline that is divided in different blocks, and each blocks are coded with a different color. The pipeline is an extension of a adversarial network where two models are trained at the same time in a sum-zero game. The first model is a super resolved network that taking input the low-res images and generate super resolved images. The second network is a discriminative network that taking input the output from the super resolved network and the high quality images from a target domain and try to distinguish images from these two sets. As I mentioned before, this is not enough since the low-res images and the high-res images, they are not aligned. So we had to include this extra cycle consistency that is based on the Voronoi vectorization, and I will explain this on the next slide. And finally, we had a regularization term to better train the network. To understand the cycle consistency, I need to introduce the physical principle, how these endomicroscopy images are acquired. Specifically, I'm going to concentrate on the probe-based confocal laser endomicroscopy that consists in a bundle that has a size of a few millimeters. In this bundle, there are between 10 to 30,000 fiber positioned irregularly inside the bundle. Oops. Yeah. Then each fiber acts as a single pinhole, and that means that we have 1 pixel for each fiber. Once we collect all the all the value from all the fiber, we have a vector that we refer as a vector low-res. And from the vectorized low-res, we can reconstruct the images, interpolating the value from the center of the fiber position to a regular grid. Now, starting from the output of the super resolved network that generate a patch, we can inverse the process of reconstruction and generate back a low representation of this page, and impose that this low representation is exactly the same of the initial low representation of the low-res images. And this is our cycle consistency. More specifically, this is based on this Voronoi vectorization. How it works? Starting from the fiber position, we create a Voronoi diagram that is a partition of the patch in different regions. And these regions are created according to this fiber position. Then, using the patch, we average all the pixels in each region, simulating the point spread function of each single fiber. Then we created this Voronoi vector, and we add a padding and a normalization to make the process parallelizable and faster in training. And we impose through a loss function that these two vectors will be similar. More formally, our training is a min-max problem where the loss function of the super resolved network is minimized, and the loss function of the discriminate network is maximized. Here, the two networks have two different set of parameters, and the loss function of the superresolved network is a composition of three terms. The first term is the regularization term that is irrelevant for this talk, and I'm not going to discuss about it. The second term is the mean square error between the two vectors that I mentioned in the slide before. And the last term is the adversarial loss function that is based on the probability of the discriminative network to find that the generated image is belong to the target domain. And we want this negative in our loss function. Instead, for the discriminative, and this because the super-resolved network have to fool the discriminator, and for this reason, there's the minus sign. Instead, regarding the discriminative loss function, we want to optimize the fact that the loss function, the network can recognize the images from the target domain and the images produced by the super-resolved network. In our experiment, we use a 238 video sequence that correspond to around 800 video frames, and this comes from 143 patients in two different regions, colon and esophagus. And for the assessment of our approach, we use quantitative and qualitative analysis. For the quantitative, we use three different metrics and a final total score that is based on these three metrics. For the most study, instead we ask 10 medical imaging experts to evaluate 20 images each and assign a score on 4 different questions. The first experiment was to compare our approach with state-of-the-art, with other state-of-the-art solutions that are both supervised and unsupervised. And we show that our approach provides the best total score. The second, the qualitative result instead show that our new approach, we basically compared this new approach with our preview approach that is based on unsupervised training, exploiting synthetic high-res images generated by video registration approach. And we show in this mouse that the new approach improve the artifact. There are no more artifacts with respect to the preview one. And in conclusion, the final preference is this new approach. In conclusion, I hope that the projector works fine. I'm going to show you a video to show that effectively our approach does something. I think it's not so visible. But basically, the first frame in the video is the low-res images. And gradually, these images is super resolved. And you can see that the noise is reduced, the contrast is improved, and the artifact has somehow reduced. In conclusion, I would say that this framework is useful when each time that perfectly aligned images of low-res and high-res are not available. And with this, with our qualitative and quantitative analysis, we show that effectively we can produce super resolved images that can improve the diagnosis. And with this, I want to conclude and thanks all our collaborators and you for the attention. And I open to take any questions.
So we have some time for questions.
Thank you for your presentation. I was wondering, you used standard image datasets as a comparison for high resolution for the discriminator. And I was wondering if you would use some kind of high resolution medical image dataset, if that could perhaps even increase the performance.
I didn't put the slide with all the domains that we tried. But basically, we tried different domains. And we realized that for some reason, the natural image domain seemed the one that performed better. And probably it's due to the fact that we use a contrast and contrast measurement, but it seems that natural image is the domain that provides the best result. But we tried also other domains.
Thank you.
You're welcome.
Any other questions? So I guess we can move on to the next speaker. Thank you very much.